All right, people, let's first discuss the difference between strong acids and weak acids. So we know our 6 strong acids: hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric, perchloric. Let's take our quintessential strong acid, HCl. What it means to be a strong acid is that it dissociates completely in water. That means that after I put it in solution, it will be no more molecules of HCl. It will only be ions of H plus and Cl minus. The reaction goes to completion. So if we were to draw little particle pictures for it, here's our HCl before it dissociates. Sorry, these are all supposed to be the same size. And then after it dissociates, we have no more HCl's. It's all H plus and Cl minus ions. Like such. Weak acids, now remember, hydrofluoric, it's very tempting to call it a strong acid, but it is not. Weak acids do not dissociate completely. So some of it will fall apart into H plus and F minus, but most of it's going to stay as molecules. So particle pictures are going to look like this. This is before, and then after, most of it's still going to be in molecules. So a very small amount will dissociate. That's the difference between a strong and a weak acid. So in strong acid problems, the concentration, so if you had 3 molar HCl, that's also 3 molar H plus. So the pH is going to be the negative log of 3, which is negative 0.41 something or the other. You cannot do this with HF. So if I have 3 molar HF, it does not equal 3 molar H plus. We have to approach these problems in a different way because the only parts that affect the pH are the H pluses floating around in solution. So we need to calculate what that will be. So let me rewrite my chemical formula here. Has a double arrow because this is an equilibrium. It does not go to the completion. It does not lean towards the right. It leans towards the reactants. Like such. So they might ask you for the pH of a, let's just stick with our 3.0 molar. If they tell you I have a solution that is 3.0 molar HF, what is the pH? Believe it or not, we have all the information that we need because you have reference materials where you can look up the Ka. Ka is 3.53 times 10 to the minus 4. Whenever we see concentration, we think of ice chart. The initial, the I in the ice chart for acid-base problems is always 0 because we're talking about before any dissociation has occurred. For this to not be 0, we'd have to be talking about a common ion problem, which is a little bit different. So for every one piece of HF that dissociates, I will get one piece of H plus and one piece of F minus. So at equilibrium, my concentration of HF is going to be 3 minus X, and these guys are each going to be plus X. So remember, K is products over reactants. K is the the equilibrium constant. Ka is the acid dissociation constant. It is the same thing. It's a equilibrium constant. So the general form of every weak acid is concentration of H plus times the concentration of A minus over HA. In this case, it's H plus, F minus, HF, like such. So I'm just going to put little squares around our general forms. So now let's plug in. We've got our general form of the acid dissociation constant for any weak acid, and that's our Ka. Now let's plug in. Each of these is an X, and HF is a 3 minus X. So 3.53 times 10 to the minus 4 equals X squared over 3.0 minus X. Now this could be a complicated problem where you would have to do the quadratic formula, blah, 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 blah. But we're going to make use of a specific skill right here, right now. So pay close attention to this. This is a skill that can be used in acid dissociation constant, base dissociation constant, all equilibrium problems. In that, I'm going to expand out this number here so we can actually visualize how small it is, 0.000353. If you put into your calculator 3.0 minus 0.000353, you would get the answer 3. So what we're going to use is a special tool called the 5% rule that allows us to ignore the value of the contribution of this X. So we don't get rid of all X's, we only get rid of that X. We're going to bank on the fact that the value of X is going to be so small that it is not going to change the number 3 by any measurable means. So my problem now becomes, I'll go up here, 3.53 times 10 to the minus 4 equals X squared over 3. Now this is an easy problem to solve. So in your calculator, when you solve for X, you get a value for X of 0.0325. Now we're going to check that we made an okay assumption by getting rid of this X right here. And this is called the 5% rule. So the 5% rule is when you take the value of X, compare it to the initial concentration, multiply it by 100, and it's got to be less than 5%. So let's put a little box around this. This is my 5% rule. I'm going to give you a little dead giveaway. All of the problems we're going to do are going to pass the 5% rule. So I'm just teaching it to you because otherwise I get lots and lots of kids saying, well, how do I know if I can ignore it or not? So let's see if it does pass the 5% rule. Our value for x is 0.0325. Our initial concentration given to us in the problem is 3.0 molar. You type it into your calculator, and I get 1.08%. That is much less than 5%, so we're going to say it passes the 5% rule. Now let's go over here and see what all of this tells us. Well, our concentration of H is actually the value of X. So the concentration of H plus in this problem is 0.0325 molar. Then I can get the pH with the negative log of 0.0325. And the pH in this solution is 1.49. So because of the fact that we're going to ignore all these minus x's, I can also get a general form. And anytime I'm doing the pH, it's always going to be x squared over the initial concentration. So this is another thing that we can count on every single time for a weak acid. X squared over the initial concentration equals the Ka. And X is going to be the concentration of H plus. Therefore, the pH would be the negative log of X. Those are all things you can count on for weak acid problems. I'm going to do another one that actually has 2 hydrogens in them, because this will be helpful too for you to understand the fact that 2 hydrogens and 1 hydrogen are done the same way. And the reason is that H2CO3 may have 2 hydrogens, but those 2 hydrogens are not created equally. They're going to come off one at a time, so we would have to do their Ka problems one at a time. And I'm going to show you this is still going to end up being x squared over the initial concentration. Let's pick an initial concentration of 0.875 molar. I can go to a chart, which I have on the wall here, and you can see that you can find carbonic acid. It is 4.30 times 10 to the minus 7. The hydrogen carbonate ion, or the bicarbonate ion, is 5.61 times 10 to the minus 11. You can see that there is a 1,000-fold difference between their Ka, so they're not even in the same ballpark. So 4.3 times 10 to the minus 7 is my Ka. That's going to be given to you in the problem, or you're going to be given stuff to calculate it, or you can look it up. This line, the change line, is always going to be the same in these problems. Minus x plus x plus x. We would never pull both of those hydrogens off of the carbonate ion at the same time. They're not created equal. Remember, let's just ignore this little contribution right here. So it becomes 4.30 times 10 to the minus 7 equals x squared over 0.875. So x squared equals 3.76 times 10 to the minus 7. And x becomes 6.134 times 10 to the minus 4. Remember, that x value is actually the concentration of H+. I'm going to do that 5% rule for you one more time just so you recognize why. So remember, the 5% rule is when we compare the value of x over the initial concentration. And see if it's less than 5%. And it's actually 0.070%, which is much less than 5%. So we were good and well within our rights to ignore the contribution that x has, or the change that x would make to the initial concentration, the change that x would make to the concentration of carbonic acid. My pH would be negative log of 6.134 times 10 to the minus 4. And I get a pH of 3.212. So I want to point out, you can have a concentrated weak acid, or you can have a dilute strong acid. Strong acids, if you have a concentrated strong acid, you're going to have a super low pH. If you have a concentrated weak acid, you're going to have a pH around 2. You have a dilute weak acid, you're going to have concentrations that are, between 4 and 7, so on and so forth. So strong acids and weak acids, if they have the same concentration, the pH of the strong acid will be lower because of the percent dissociation.